You're getting close to the end of the semester. I suspect you're excited about that. And you're starting to think about, how do I prepare for the thermodynamics final exam? So I'd like to just give you some ideas on preparing for the exam as you sit down and spend some significant time preparing to maximize your performance on that final exam. So this is a crash course. I've tried to funnel down the most important ideas. And in this little presentation, you're not going to find the first formula. I'm going to give you a suggestion on how to follow up on that, but this is more idea-based. So you can plan your time. What are you going to do on the exam? What can you expect on the exam? Now, depending on your section, there's a number of possibilities here. One is you're allowed to create a formula sheet or sheets. That's okay. That's all right. You may be provided a formula sheet. It's my hope that you'd be able to see that formula sheet before you walk into the exam. And then there are other sections. For example, if I'm teaching the class, there is no formula sheet. And so I want to remind everybody that this is your best formula sheet. What you have in your head ready to go out of your own, more than memory, it's something you've learned as a result of doing the homework problems, paying attention in class, taking notes in class, and basically putting all the material in the class together in your head. So your best formula sheet is your head. Okay, the next thing, now you're going to walk into your exam. You're going to be a little nervous. All of us are nervous when we take tests and are measured on our performance. How will you get started and how will you monitor your time? Well, of course, you're going to bring in some type of either a watch or your smartphone to monitor your time. And you want to keep an eye on the time you're allowed and budget your time for X problems, whether it's 3 problems or 4 problems, however many it is, you want to think about budgeting your time. And so how will you do that? The first thing you're going to do is scan each problem quickly, not necessarily read very carefully. Scan each one to get a general idea of what's going on in each problem. And that will help you determine the order in which you work the problems. That's up to you. In my case, when I was a student, I would work on the easiest problems first that I could bang out to maximize my partial credit the best, okay, and then save the hardest problems for the last. But the way you attack and order do the problems, that's all up to you. Okay, so you've thought about the order in which you're going to do the problems. So you've selected one of your problems to work on. What will you do? What are your steps in solving the problem as accurately and quickly as you can? You're going to read the problem carefully. What are the key words and clues? This is where you're doing your homework problem is really going to pay off. Doing homework problems experience will pay off. The key words and clues given in a problem statement is going to govern the time that you're going to spend on that problem. There, an awful lot of times there are keywords or clues that make certain answers a snap, a 0, and you'd write that down, maybe explain it. Okay, read the problem carefully, look for keywords and clues. All right, what's the next thing you're going to do? After you've read that problem, you will start with a sketch. I am seeing that in a number of sections, sometimes test problems come with a sketch. That's not the case if I'm teaching the class. There are no sketches that I give, okay? Some sections, you're going to get a sketch. There's no need to redraw the sketch. I don't feel any need to redraw a sketch if it's provided. If none is provided, you must start with a sketch, okay? What does that mean? You're going to draw a system setup. Is it a piston and cylinder? Draw that. Is it an open system turbine or a compressor or a pump or a cycle? You're going to want to depict that somehow. You're going to show your states 1, 2, 3, 4, 5, whatever it is, show the states on your sketch. Next, that's not the end of it, is it? If it's a closed system, you're probably going to need to draw a pressure volume diagram. Really valuable for closed systems. I hope you remember why. If you have an open system, the chances are mighty good that a TS diagram near the end of the semester, a TS diagram is really going to be needed for you to see how to solve the problem, even if it's not assigned. Draw a TS diagram if you have an open system. That's going to help you not waste your time. Okay, the next thing after you've read the problem, you've drawn a sketch, then you're going to really decide, is it an open system or is it a closed system? My suggestion is write those two words down. Write down open system or write down closed system. That will buy you some measure of partial credit on the problem. It also governs your governing equations, doesn't it? A lot more about that in a second. The next thing to decide, what's my substance? What substance do I have? And remember, for this class, it falls into two categories. Either I have an ideal gas, like air, nitrogen, CO2, or is it a phase change substance, like steam or water, ammonia, refrigerant 134A? You get the idea. So it's one or the other two of those categories. Now, I'll remind you that evaluating the numerical values for properties is a key to success in this class, and your ability to get those properties quickly fully depends on how much you understand and have done the homework problems. Okay, you've decided on the open system, closed system. You've decided on your substance. What are the fundamental equations that will enable you to numerically evaluate the result requested? Notice here, I've written down the word formulas and I put an X through it. That's because simply writing down formulas is probably not going to buy you much partial credit, especially if formulas don't apply to the problem at hand. So remember, we're looking for fundamental equations to really understand that you understand what's going on. So what are examples of the fundamental equations? Well, if you have an ideal gas as your substance, the equation of state is clearly a fundamental equation. P times little v equals RT. There may be other, remember, P times capital V equals MRT, and on. But that's a fundamental statement about an ideal gas. Okay. The continuity equation is a fundamental. More on that in a second. The first law, or conservation of energy, is a fundamental equation. That's where you would start, not just start writing down a specialized formula. And also, in terms of fundamental equations, a type of process is the keyword isothermal given in the problem, is a keyword isentropic given. Let's see, what could be a synonym for isentropic? The two words reversible and adiabatic are the same as saying isentropic. Is the process adiabatic? And on. But you get the idea. Those are the fundamentals associated with getting a numerical result for the problem, not just applying numbers into formulas. Okay, next, so you've got your fundamentals written down, maybe a few words, you got your sketch, you got your fundamentals. Then the next step is working on the numerics of the problem. Strongly recommend you do those first two things, sketch and write down fundamental relationships, equations, before you start working on numerics. Why? What kind of things can you strike out of the fundamental relationship? Is the process adiabatic? If it is, it's no heat transfer. You strike out Q. Is it a closed system with a rigid vessel? Let's see, closed system, rigid vessel. A lot of homework problems. No work is done. I'd strike out W. That's going to get you some partial credit. Next step, property lookups. Chances are good you're going to be interpolating in your exam. You want to clarify what you're doing with your interpolations, particularly for phase change substances, sometimes for the ideal gas air. Okay. But recognize again that evaluating the numerical properties H, U, specific volume, V, little s, entropy. Those are the keys to success in this class, okay? Property lookups. And then finally, ideal gas computations. If you have an ideal gas, what can you do with the ideal gas equation of state that doesn't even involve property lookups? It's simply the fundamental ideal gas equation of state. Okay, now this is going to be a little self-quiz for you. I want you to be honest with yourself. You don't, nobody else in the room. You're strictly thinking about yourself. Little quiz for yourself to get ready for your good performance on the exam. I know by heart the continuity equation. So true or false for yourself. Remember that there's two statements of continuity. One would be for a closed system. One would be for an open system. Do you know the continuity equation for both of those? It is my hope that you do. As an undergraduate, I would say I really knew the closed system continuity equation. I was pretty good on steady state, steady flow, open system. Transient flow, not so much. I know by heart the first law of thermodynamics, in other words, conservation of energy. Can you state right out of your head, could you say it or write it down quickly on your test sheet? The first law for a closed system. What could you strike out? What terms could you strike out from there? Could you write down the first law for an open system? Steady state, steady flow with one inlet and one outlet. Let's say you have a pump or a compressor or a turbine or a throttling valve or a nozzle. That's going to be, all those will be steady state, steady flow, one inlet, one outlet. Can you write down the first law for that type of problem? How about an open system? Steady state, steady flow, multiple inlets and or multiple outlets. I can think of some homework problems where you had a mixing chamber, a mixing vessel, where there were two inlets and one outlet. Can you immediately write down the first law for a situation like that without going to a formula sheet? Now, finally, first law for an open system undergoing a transient process. I will be surprised if you have this type of problem on the exam, but I have seen some sections where professors include a transient open system problem as one of the problems. Now, I'm going to have to openly admit, as an undergraduate student, I did not have the open system transient process first law right in the top of my head. Even I would have needed to have gone to a formula sheet for that. So I'm going to openly admit that to you. Okay, second law, little tougher. Okay, what kind of things did we use the second law for? We were able to determine if certain proposed processes were possible and reversible, possible and irreversible, or simply impossible. And how did we do that? Just a little memory refresher. We got good at learning what were some special things about the Carnot cycle. The Carnot cycle taught us some things about the best that could possibly be achieved. And we compared our proposed process or cycle to a Carnot or reversible situation. And that's what enabled us to determine if a proposed process or cycle was reversible, impossible, irreversible, impossible, or impossible. So Carnot cycle refresher, very important. And remember, there's three types of cycles that you studied. A power plant cycle where net work is produced, a refrigeration cycle that requires work to run, but the objective is cooling from a cool space, okay? And then a heat pump cycle. That's where the objective is heating a warm space by pulling heat from a cold space at the expense of doing work. So there were three measures of performance. Let's see. Power cycle, thermal efficiency, eta, Greek letter eta. Refrigeration cycle, coefficient of performance, beta. And heat pump, coefficient of performance, gamma. Okay, so it's my hope that you have that off the top of your head. And then equipment efficiency. Remember, there's definitions, and I've claimed you should be able to figure this out on the run. What's the definition of steam turbine efficiency? What's the definition of compressor efficiency? Pump efficiency. That's different. That's not a cycle, is it? That's a process. So that's different than the thermal efficiency of a power plant. And then I sneaked in the bottom right part of the slide, I'm seeing that a number of professors are asking for either entropy production, Greek letter sigma for a closed system, or entropy production rate, sigma dot, for an open system. So that's something you're going to want to refresh your memory on. It's very powerful, but that would definitely be a memory refresher if your professor, instructor says that's going to be covered on the exam. Okay, notice how really there were no formulas in this crash course, were there? So that's what I want to do is chase you to a longer video that I've called Things We All Know About Thermodynamics, that I've dedicated to my top professor and supervisor, inspiring individual, Dr. Jones. I'm taking 42 minutes to really slide by slide go through the things we all should know about thermodynamics as we're finishing our course. And this might help you in preparing your formula sheet if you're allowed to do that. 42 minutes. You can get a static copy of the PowerPoint slides so you can go over slide by slide if you wish. And so anyway, that's my recommendation, that you take 42 minutes to browse this video as a reminder of really a lot of the details, a lot of the fundamental equation details of things I would expect you to know as you're finishing this class. Okay, recap. Let's recap. You're taking your exam. Start with a sketch. If you're given a sketch, you don't need to redraw the sketch. That's not worth anything. But if you're not given a sketch, start with a sketch. Okay. Chances are good that you might not be given a PV diagram or TS diagram. You'd want to include those with your own pencil and paper. Show and explain your work. Don't just write down numbers. Don't just write down formulas. You need to add some words as you're working down the page. Start each problem on a new page as a courtesy to the person looking at your exam. Remember, you don't want to make that person mad, right? You want to make that person's job as easy as possible in evaluating your work. So work down your page, not gunshot, all around the page, and start each problem on a new page. Now, if you've looked at my videos, if you've joined online, the best advice that I received as an undergraduate, as a graduate student, and then even into my own career, when you're stuck and you just don't know what to do, that can happen in an exam, can it? Write down the first law of thermodynamics. Write down the first law. Simply writing that down and looking at it can help inspire you quickly to see how to get started. It helps you see what do I know in this first law? What do I not know is what I'm trying to find buried in the first law. So writing down the first law can really help you see how or where to start on solving a problem. Okay. And you may have seen this before. Luck is a matter of preparation met by opportunity. So this exam is an opportunity for you to perform well, to show how you can perform. And so knowing the material, there's your head, knowing the material, plus your ability to perform on the test. That's going to be the result of your working very hard on the homework problems. It's my hope that your instructor gives you problems on the final exam that are representative of homework problems. The sum of that, your knowledge plus your ability to perform, is going to equal a good grade. And that's what you're looking for, right? As well as being prepared to begin to be a practicing engineer. So I wish you all the best for really good performance on your exam. That's up to you and your preparation. You've been preparing the entire semester for this, and I wish you all the best for good success beyond this class as well. So good luck on the exam. Good luck on your subsequent classes, and then beyond as you begin working. And I'm trying to figure out how to stop recording.